Hi, I'm Hamilton, doing it the Kiwi way. This is Lab 1 concerning the FPGA implementation of the finite state machines. This is part 2, implementing the power button and the draw action on the Fisher Paykel Draw Dishwasher. We're going to implement it onto an FPGA using the Moore Finite State Machine as per the following image here. If the display is off and we open the drawer, display goes on. If the display is on and we close the drawer, the display still stays on. If we open the drawer and the display is on, display still stays on. If we press the power button when the drawer is open and the display is on, the display goes off. When we close the drawer, the display still stays off. Open it and the display goes on. Close it and the display stays on. You press the power button and the display turns off. Our Moore state machine is what we've designed to implement this action. We've implemented the reset button as well. So here's state 0, which we start off in. If the power button is pressed and the drawer's not open, or the power button is pressed and the drawer is open, we go to state 1. This is equivalent to saying just the power button is pressed. When we're in state 1, we automatically switch on the display with V equals 1. To move into state 2, we have the power button is not pressed and the drawer is open, or the power is not pressed and the drawer is closed. This again is the same as saying not P. Then we move into state 2. And we can move into state 3 if the power button is pressed and the drawer is open, or the power button is pressed and the drawer is closed, and that is equivalent just to saying P. Then we're into state 3. If the power button is not pressed and the drawer is not open, we'll move into state 0. If the power is not pressed and the drawer is open, we move into state 4. And here in state 4, we move into state 0 if it's not the power button and not the drawer, or we move into state 1 if it's the power and the drawer, or the power and not the drawer, which is equivalent again to saying power. We've used some formatting notations here. P equals the power button. When it's pressed down, it equals 1. When it's up, it's equal to not P or 0. When the drawer is open, it's equal to 1. When the drawer is closed, it's not D and it's equal to 0. Our combinations here are separated by a comma instead of me putting them on a new line. The commas can be considered ORs. PD reads P and D, so P not D, or not PD reads P and not D, or not P and D. 00 reads not P, not D, or not P or and not D, sorry. We've written up some VHDL code here, and I think I'll go through and show you that now. I'll explain what the code is doing here. We've got a clock that is required. We've got our reset button, which we've implemented. We've got our P in. The P in is effectively our power in button. The D is when we open or close the drawer, the D in. The V out is the output of the display. We'll show it as a LED. And the P out is the output to show the status of the P button being pressed or not. We also defined another one where we have our display of our state. That's a logical vector 2 down 0, 3 bits. That's the end of our entity, our configuration. I've just put it in here because I might be implementing a Mealy machine later on. And this just merely tells it that we're going to implement the Moore architecture when we compile this hardware description language. I've set up a couple of signals so it's consistent with our diagram. I'll just show you. So P, D and V. And then I've defined our states with this enumerable type called state. And we've got state 0, state 1, state 2, state 3, and state 4 as per the diagram you can see down there on your right. Now, P is being assigned not P in, because P in is active low. So when the button is not pressed, we get a 1. We want to get a 1 when the button is pressed, and this was what it will do for us. The draw is assigned draw in. These are internal wires. V out is to display the status of our display, which will be a LED. P out is just telling us what the button is, and that should not be not. It should be, oh yeah, no, we'll do that P, sorry. Then we've got our process. This process executes only if the clock is going, if there's a change in the clock or there's a change in the reset. So for the reset button, or we've implemented it as a switch, is set to 1, will automatically go back to state 0 regardless of the clock. If the clock is on the rising edge, we'll go through and execute this part here. So when state equals 0, if P equals 1, then we go to state 1. Else, if P is not pressed and the drawer is opened, then we go to state 2. State 1, if P is equal to 0 or it's not pressed, we'll go to state 2. State 2, if P is equal to pressing the button, then we'll go to state 3. When we're in state 3, this one's a little bit of a tricky one. We need to decide whether to switch off the power display or keep it on. So what we do is if P equals 0, it's not pressed, and the drawer is closed, then we'll go back to state 0. Else, if P is not pressed and the drawer is open, then we'll go to state 4. State 4 will have the display off. When we're in state 4, we'll go P equals 0 and D equals 0, then we're off to state 1. Else, if the power is on, we go to state 1. Sorry, I said state 1 up here, I think. I meant state 0. And then we go into our process environment for the states. This only executes here if the state changes. So when we're in state 0, we have our display off. Also, I'll display the state status as 000 on our LEDs. When we're in state 1, we'll put the display on, and this is the state record 001, and we'll go through and follow the following cases down there. So once all that's done, we'll compile it. While it's compiling, we'll go to our pin planner, if it lets me. Yes, it does. This is a pin planner for the DE1 SoC FPGA development board from Terasic. We've got our clock assignment here, a drawer assignment when we close or open the drawer, our power assignment when the power button is pressed on or it's not pressed, and we display the power button. We've got a reset switch that we've defined, and here is our states that we'll display out on LEDs, and also where the display is actually on or off will also be displayed on an LED. We're almost finished. So while we're compiling, I'll get my pin planner open. Almost there. I could open it now actually. Here's our pin planner. And see, I've selected my DE1 SoC. and we've completely finished. We've got 12 warnings. They can be explained, but won't go through that. So right now, let's go and see our FPGA device. And we'll program it. And that's done. So now we'll go through, I'll just tidy up the screen a bit. Whoops. So here's our FPGA device. I've implemented this as the power button. I've implemented this as our reset switch. So we always stay into state 0. When I press the power button, we're in state 1. The display goes on and the second LED there shows that the power button is pressed. When we release the power button, we go into state 2. We can open our drawer. It has no effect on changing the states. Just make sure I've got the right button. Now we go off into state 3. The drawer is now open and we're in state 3. The display is switched off. Release it. Now we go into state 4 because the drawer is open. Now we can close the drawer and we go back into state 0. If we open the drawer, we go straight into state 2. The reset button throws us back into state 0. Where no LEDs are displayed here at all. And no matter what we do, we always stay in state 0. And the display stays off because we're in reset mode. We'll switch it off and reset. And we can open the drawer, press the power button, and we reticulate through the states. Also, what we can do is press the reset button and have the drawer open at the same time and see what happens. I'm still in state 0. Switch off the reset and we'll automatically go into state 2 and the display is switched on. Oh, can you see it? Yeah. Well, I think that about explains it. What I'd like to show you briefly is the setup for the environment. Let me switch that one off. And I'll hide the display capture as well. Whoops. This one here. In the project settings, bear with me. Oh, device, sorry. Planner and pin options. Here I've changed it from weak pull-up to as input tri-stated so it doesn't show dimmed LEDs. Cancel over that one. Also, what I've done is I've simulated our actions on a simulation, waveform simulation. We can run that simulation. So this is a functional simulation. Where am I? There we are. And this is when the reset button is pressed. You can see we'll automatically go into state 0 as soon as the button is pressed. And you can see it here as well. And we can zoom in on an area. When the power button is lit up, or when we press the power in, but this is the inverse. We wait for the clock. The clock sees a 1 here and automatically goes into state 1. On the rising edge of the clock here, we can see that the power button is no longer pressed and we move into state 2. Now we're in state 2 where the display here is still high and we open our drawer, the light still stays on. And here the clock sees that we have pressed our power button again and the drawer is still open. We go into state 3 and the LED or the display goes off. Then we go into the reset, and of course we go straight into state 0. Well, there's quite a few challenges here doing this simulation. I hope you enjoyed it, and waiting for the next one where we'll implement all the graphical user interface options available on the Fisher Paykel Draw Dishwasher.